So my thesis topic is designing interactive systems for community citizen science. And during my talk, I will introduce what's the concept of community citizen science first. And then I will talk about research questions and my contributions. Then I will talk about two projects. One is the Schöninger channel, which is the air quality monitoring system. Another one is Smell Pittsburgh. And then I will conclude with design implications. So citizen science in general refers to empowering amateurs and professionals to form partnerships and produce scientific knowledge. And I want to emphasize the importance of partnerships. Traditionally, when people think about science, it's like scientific projects conducted by experts in research institutes. But right now, citizen science is really different because it emphasizes the collaborations between amateurs, which is our common people or citizens, and also the experts. In general, citizen science has two strands. One is more research-oriented, another one is more community-oriented. And I'm going to use projects to explain this. So the research-oriented one, for example, can be the Galaxy Zoo. So that's the project for classifying a lot of galaxies online. And in this type of projects, one really important thing is the research question is often defined by scientists. So it's asking the question about how common people can help scientists in collecting a lot of data. Usually these type of problems are really large that scientists cannot solve this alone. So they invite citizens to participate in this. The second strand is called community-oriented project. And this is actually what I care more about in thesis. For example, this is called Louisiana Bucket Brigade. So that project was started by an attorney on about 1995, when the attorney was working on suing a local polluters. The attorney worked with several engineers to create these low-cost sensing devices. So citizens can take the device to collect air quality samples and then use that as an evidence. So they can take that air back to the lab for further analysis. This type of project is really different than the research-oriented one because now the research question is defined by citizens. And we are asking the question right now about how professional scientists can help citizens. So you can see these two approaches are really different. Okay, so we can in general think about citizen science from three different aspects. First one is the value, so which is the one that I just described. It's about scientific research versus the participatory democracy values. The second dimension, we can think about it as participation levels from citizens as tools to citizens as scientists. So in the Galaxy Zoo project, it makes more sense to treat citizens as sensors to provide labels for a large amount of galaxies. And in citizens as scientists part, it makes sense for doing this because communities has local attachments to their concerns. So actually it makes more sense to treat citizens as scientists that can help or design the system features with experts together. The third dimension is called governance structures. Usually research-oriented project because the research question is defined by scientists. So usually it's top-down. It's like from the academic institute or governments. Another one, the community-oriented part, is more grassrooted, so it makes sense to use the bottom-up or multi-party structure. Okay, so my research scope, which is the community citizen science, is the community-oriented one that I just described. It focuses on empowering citizens to produce scientific knowledge. One really important property about this type of problem is called wiki problem. So usually the problem community citizen science is facing is complicated. For example, air quality problems. This type of problem is at a really large scale. Also, it has no clear definition. In every city, the conditions are really different. Like, for example, the number of pollution sources, the scales, the structures between the communities and the regulators. Also, wiki problems, they are really depend on context, in which in every city is different. And then it has no room for trial and error. For example, if we want to deploy a system in like one city, we can't just deploy it and say like does it work or not? Because every time when we deploy the system, it costs a lot of financial resources and labors. So there's no room for trial and error. Also, there is no right or wrong solutions to these kind of problems. So because of the complexity of this type of problem, we need to collect a lot of evidence to support and produce the scientific knowledge. And that's why we need the information technology for doing this. In general, empowering citizens to form scientific knowledge with information technology poses 3 challenges. And here are 3 challenges. The first one is data quality. For example, it is really difficult to have people monitoring air quality 24/7. So we need to have ways to somehow automate the data collection process. The second one is during the collection. Usually we collect a lot of like personal information, like your GPS location. Somehow we need to anonymize them. The second challenge is related to communication. For example, if we collect a lot of data from multiple sources, how do we visualize them together? And the second one, besides just visualizing the data, how can we further extract knowledge from it to use it as evidence? The third one is called evaluation metrics. So how do we measure the social impact after we deploy the system? And then this is my main research question. How can we design interactive systems with visualization, crowdsourcing, and AI techniques to support life cycle in community citizen science? So now I'm going to explain the life cycle. So remember I talked about the wiki problem. And the wiki problem is what makes it hard to use traditional software design principles to do this. And this idea is actually inspired by architecture design. So when architects, they are solving problems like building a public space for communities. This type of problem is also a wiki problem. The architects, they use buildings to solve this type of problem. And now I'm using interactive systems. So that's the similarity of it. And when architects design buildings or like the public space, they need to understand community's needs. Also, when they build something, it is important that they keep observing the behaviors of how people use the space and then change their design methods accordingly so they can use it for another design iteration. The idea is inspired me to consider the cycle. So the first step is how do we initiate the community engagement? Initiation, we can like visualize data, and also we can break a large task into small tasks for crowdsourcing the data. The second one is called maintenance. So after we initiate the engagement, how do we maintain the participation? For example, how do we automate repetitive tasks when people are using the data to collect evidence? Another one is, can we actually extract knowledge from the data and show it to people? So it is important for this step because a lot of citizen science projects, they stop or like died in the middle because they have no like enough participation. The third one is called evaluation. So after we deploy the system, how do we evaluate the impact of these kind of systems? For example, we can measure behavioral changes or measure attitude changes. And then this evaluation then can provide design insights or design implications that inspires another design iteration. So that's the idea of the cycle. And here are my contributions. My contributions are to the sustainable HCI field, which studies the intervention of using interactive systems to influence the attitudes and behaviors towards sustainability. There are 2 types of contributions. One is methodological contribution. So I have 4 systems in the thesis. And after that, I provide empirical and generalizable design implications. These are the 4 systems. And during this talk, I will briefly mention the air quality monitoring project, which is the Shiningo channel. And then I will talk about the smell Pittsburgh in more detail. So current research on designing interactive systems usually focus on either human-generated or machine-generated data. And these 2 types of data, they are really different. And then they all serve as a fragment of evidence. For example, human-generated data, they can show how residents are affected by local issues, but they are typically hard to quantify, and they are typically noisy, these data. For example, Ushahidi is a platform for crowdsourcing a lot of crisis information online. So people can send information via SMS, like text messages or emails. Then the information can be posted on the website. So this type of data is really useful when the mainstream media is filled with doubts and rumors, and then citizens can submit like the actual information to the platform. For example, there's like post-violence after the election. And then machine-generated data, it is good in providing temporal dense information, but it fails to explain how residents experience the environment. For example, this is SPEC sensor, so it's an indoor air quality sensor. This type of sensors you can place it indoors, and then you can, when you cook, you can look at the sensor readings, and you can see, okay, if the sensor reading is rising, then we know we need to turn on the fan. So that's like how we use machine-generated data. So now I'm going to talk about an example about how to integrate a lot of type of data, which is the air quality monitoring system. It integrates images, sensor readings, and also smell reports from the community. So back a long time ago, we worked with ACAN in solving a local pollution problem. So CMU is there, and then we work with the community, which is on the west north of Pittsburgh. So the community suffers from air pollution problem for a long time, and that a lot of the air pollution comes from the coke refinery there, because when they emit pollutions, when the wind blows through the community, then they get all the pollutions. So we want to help them to collect strong evidence, and this evidence are actually data-driven. So they are driven by sensor readings and cameras. We help people to deploy cameras in the communities and sensors. And these sensors and cameras are actually provided by us, but the locations are provided by the community members. And we want to present them to the government or media and raise the public awareness of air quality issues. And these are like images. Okay, so now I'm going to give a demo of the system. In here, you can see there's a zoomable and panable time lapse. So you can pan and zoom. There's an area there that has a lot of emissions, and we have a computer vision algorithm that is looking at that location. So instead of having people looking and checking all the video frames, we now have the computer checking. There's calendar and cameras. And there are smell reports that we get from community members, and also the sensor readings. That's the smoke detection part. So this algorithm allows people to just quickly check which part has smoke, so they don't need to go through all the images, because we have years of data, and it will take a lot of time for people to go through all of them. And they can also fast forward. So as you can see, you can fast forward through this without seeing the entire video. And then, to go further, we actually provide smoke images from the system, so people don't really have to generate manually. So system is able to provide a lot of images, and people can just choose one, and then put it inside a document to collect it for evidence. Okay, so this is the result. On a November 2015 meeting, we project this on a large screen in front of a meeting with the EPA and ACHD, which is the Allegheny County Health Department, which is the health department of the Pittsburgh area. And when we project this actually influences the attitudes of regulators. And the idea is the community members right now are able to tell a story by using the data. For example, they can look at the videos to say what's happening there. And then they can report smell, to say how does the pollution affect the area. The sensor readings provides the information that when the wind blows to the community, these sensor readings rises, and that's the evidence of how pollution affects the community. And then there's the smoke detection for people to collect evidence. So all these forms a really strong evidence. The community members are able to use it with their personal stories. So that's the news from the Post-Gazette. I just quoted from there. So the acting director of EPA Region 3 actually pointed at this image and said it's totally unacceptable. So you can see now the data is powerful. When people use it, they can actually change the attitudes of regulators. Okay, so the previous project is on a community scale. Now I'm going to describe a project that is operating on city scale, which is Pittsburgh. So we take the part of the smell report and we want to expand it to the city scale to empower the entire Pittsburgh citizens to submit smell reports. Just to give you an example about how bad the Pittsburgh quality is. The American Lung Association lists Pittsburgh in the top 10 most polluted cities by year-round particle pollution. So this is a map created by Albert Preston in 2016. That's the black cover map, which are a combination of pollutants, like fine particles like PM2.5. The red area indicates bad parts. So as you can see, we have a lot of red areas there. And our goal is right now to empower the entire Pittsburgh citizens to contribute scientific evidence. But now we have different type of challenges because the scale is now larger. We have more residents in this area. And also in the previous one, we have one known pollution source. But right now we don't really know which one causes the problem in Pittsburgh. Moreover, currently when people report smells to the government, it's actually not transparent and the data quality is doubtful. So this is the website for reporting smells right now. So you can go to the health department's website and then actually enter the information here inside a text box. But the problem is when people they experience the smell, asking people to report retrospectively is going to cause problem because a lot of people may forget the exact time the smell event happens, or they will forget the exact location. And if these information are not correct, then they introduce extra noise when we analyze the data. And that will cause the findings to be misleading. So that part is really important for data quality. Also, it's not transparent because when people report it, it's like going into a black box or black hole. No one knows like what happened except the people who get the report. For example, if you submit it, then it's hard to know if the problem is on a local scale or on a city scale. We don't really know how others think about this. It could be just your neighbor's problem or it could be like the city's problem. So we designed this system. And here's the demo. People can select the smell ratings from 1 to 5. And then they can also submit the source of smell, symptoms, or any comments to health department. And then when they press the submit button, actually the smell report will be sent to the health department. And there are setting parts that people can use it to provide contact information for the health department. Also, they can receive notifications like smell report alerts or air quality alerts. Under visualization, you can pan and zoom on the map. And then the triangle icons indicate smell reports. The circle icons indicate sensors. So you can click on the icons to see the detail of them. And you can also animate all these smell reports. So check the sensors on the right. When it becomes red and the wind blows north, you see there's a lot of smell reports pop up. So this visualization actually provides a way of knowing what happens there. If we just provide a static image, then it would be kind of hard to know what happens in that day. So just some numbers for comparison. On 2016, the health department collects about 800 smell reports, other complaints. But our system is able to collect tenfold increases. It's about 8,700 reports. Moreover, among these 800 reports collected by the health department, 45% of them has missing location information. But in our data, we have no missing location information, and we have all the timestamps correct. The system usage study, which is something I did after we collect all of the data, I checked the server logs and then check all the distribution of smell reports to analyze the pattern. The study showed that our user contributions were highly skewed, and most of the contributions come from less than half of the users. So that's the table that shows three different types of users. This type of user submits smell reports and also interact with the system. There are other two types of users. They either submit reports or interact with the system. When we see the data, we see that they are like 47%, but they contribute to about 91% of smell reports, 94% of the content, about 76% of the interaction events. So these interaction events, I got them from the Google Analytics. So it's a way of tracking how people use the system. Like when you click on a smell report to see what happens. Another one is if you look at the distribution. So this is a box plot. So I compute the number of smell reports submitted by each user and then plot it here. So you can see a lot of them, they are all skewed toward the zero side. So this red bar means the median. Median is 50%. So you can see actually almost like it's about half of the people. So 50% they submit less than 3 reports. That means a small amount of users contribute a lot of data. And this is actually a pattern in citizen science projects. We also found it here. Same thing happens for the interaction events. The second findings is, although our users grew over 11 months, after the soft and official launch, there was a decrease in engagement recently. So when we look at the data, the x-axis indicates the time. So I am computing the number of smell reports for that month. So I'm plotting them across the time axis. And the y-axis means the numbers. So I'm plotting the number of smell reports, number of events, and also the number of unique users. These two bars indicate the soft launch and official launch. Soft launch means we only release the system to a part of the users. Official launch means we release it publicly to everyone. We can see from the soft launch, there's usually a bump here. That's because we did a media release on this month. And also here, you can see also a huge bump. Overall, our user increases over time, but recently we found a decrease in engagement. So the number of smell reports drops, and also the number of interactions drops. I also did a text analysis of all the data that people submitted to the smell report. And the result shows that these data are highly related to industrial pollutions, especially the hydrogen sulfide. So if you look at this, that's the symptoms, that's the description and comment. And the red part that I marked here, they are related to hydrogen sulfide. For example, these symptoms, they are related to a long-term exposure to hydrogen sulfide. And the description here, you can see the rotten egg smell. That's actually the hydrogen sulfide, and also sulfur and industrial. So this idea actually inspires me to further investigate the effects of hydrogen sulfide on the communities. Okay, so remember when I talk about our system, there's a push notification. Now I'm going to describe how that works. So we want to send push notifications to encourage engagement, and we also want to use that to inform users about potential smell events. For example, you can see on the phone, this message like this, a smell event alert. It will tell you that local weather and pollution data indicates there may be a smell Pittsburgh event. And just pay attention and keep the nose out. These are the regions that we are interested in forecasting. So the numbers indicates the number of smell reports. That black dot indicates CMU, so that's where we are right now. And the regions indicates the zip code. So these are regions that we are interested in. Okay, so to enable the prediction, we want to estimate a function that maps the input to the output. The input are air quality sensors. The outputs are smell events. So that's the function that we want to estimate. So what's the input? The input is the air quality data that we get from a lot of monitoring stations near Pittsburgh. It's hourly readings because they are provided by the county. And I'm including all the readings for the current time and also the previous 3 hours. We collect about 13,000 samples. So samples are observations. So we have about this number of observations. And then that's the predictors. So we have about 195 predictors. Predictors means like particles or some chemicals like H2S or wind directions. And what's the output? That's Y. So that's called a smell event. And the way that I'm computing it is I sum the smell report ratings over the next 8 hours. And see if its value is larger than 40. Then I'll say, yes, there's an event. So it's basically yes or no. And just to give you a proportion of the yes and no, there are only 8% of the samples saying that there is a smell event. About 92% are no. So this actually, in a more technical term, is called imbalanced dataset. Means our dataset has yes and no really imbalanced. Now I'm going to describe the model to model this. So that's the f of x part. It's called a random forest. And the idea is it's a collection of trees that makes the decisions. We want to use the air quality data to predict the smell event. So idea is here. We take all the data and we first divide them into different subsets. These data include something that I just talked about, like the data provided by the county. There are SO2, CO, NO, PM, etc. For each random subset, we train a tree to describe that. And that tree is like a committee. So this is like a committee running the prediction. Each tree is like one person. It's looking at only a part of the data. So to give you an idea about how the tree works, you can look at the node. For example, it's like maybe that expert will first inspect the H2S and then check if it's larger than 0. If it's yes, then it goes that way. And then check if it's like larger than 0.1, and know if it's larger than 0.1. If it's no, then we go this way. And then eventually you will reach the end of the tree. It's like how doctors make decisions. Like when you go to a medical office, then maybe the doctor will ask you, do you have a fever? Something to determine if you have a flu. So it's like this process. And then eventually you reach the end and get a solution. So each person gives different labels and said like, yes, right now we have events. Or no, we don't have events. And then all the results are aggregated together to form the final answer. So it's like voting. And this is the distribution of smell reports over time. The x-axis means the hour of day from 0 to 23. The y-axis means the day of week. We only predict smell reports. We only predict events during the daytime because you can see here there's not really a lot of events at nighttime because people are sleeping. So when we are doing the 8-hour prediction, we do it from 5 a.m. to 11 a.m. And this covers the time from 5 a.m. to 7 p.m. because we are doing an 8-hour prediction. And the reports are concentrated around 9 p.m., like 8, 9 a.m., sorry. So now I'm going to describe how we evaluate the model. So the model evaluates by first computing true positive, false positive, and false negative. I'm going to describe how this works. So that's the top one is actually the cross-source event. It's the ground truth that we get from the data. The bottom one is the prediction. The x-axis is the time. For example, it's like 5 a.m. to 7 p.m. The y-axis indicates no event or yes, there's an event. So, for example, if we predict something happens and there's actually an event, then we say this is a true positive. That means we say yes, and there's yes, something happened. If we predict something, but there's actually no event, then we say it's a false positive. Because when we say yes, and there's actually no. If we missed an event, then that's called a false negative. Because we missed it, we didn't predict anything about it. So that's the metric that we are using first for computing the performance. After that, we compute something called precision recall here. So just to give you an intuitive explanation, precision means when our system says yes, how likely that it will be a yes. Like we can make false prediction, right? When we say yes, there could be no. And if our precision is really high, that usually means when we make prediction, then it's pretty accurate. For the recall, that means if we missed a lot of events or not. So if the recall is really high, that means we didn't miss a lot of events. So there's usually a balance between these two metrics. Like for one extreme, if the precision is really high and recall is really low, that means we could only make predictions when the sky is like completely dark or smoky or hazy. And that's not good because we are too conservative in the prediction. If the recall is really high but the precision is really low, that means we are predicting every event. So I'm sending a lot of notifications to people say, yes, there's a problem, but a lot of them could be wrong. So that's two extremes, but we want to balance them. We want to find something in the middle. And that's called the F-score measure. So it's like a combination of these two metrics, and I'm using that measurement as to measure the performance.
Just a quick clarification. You're not dealing with the duration of the event, so you still count it as correct if you predict that there was an event anytime overlapping the true event. Is that? This is more about the last slide, but.
You mean this one?
Yeah, like so those two on the left side, right? That's a true positive because that predicted event overlapped with the real event, even though it didn't. The duration obviously didn't match exactly.
Yes, I do that. Yes, that's right. So that's the reason why I do this is because that's I think it's more reflective to real situation that when there's an event happens, if somehow we can predict at one point, then I say it's good enough. Okay, then I'm going to explain now how do I evaluate this data set. So the method I'm using is called cross-validation. And the idea is we separate the entire data set into a training data set and testing data set. So testing data set is something that we use that to train the model. And then we evaluate the model on a testing data set. So we have in total 79 weeks of data. And then take the first 48 weeks, train the model, and then test the model on 1 week of data. And I keep iterating this for 31 times. And then run the entire experiment for 100 times. Then this is the final result. So the baseline that I'm using here is called always yes. That means I could make a prediction by always telling you that there's a problem. Like every day, if I tell you like there's always a problem, what's the measurement? So if it's always yes, then I'm not missing any events. So the recall is 1, pretty good. But the precision is really bad because now I'm giving a lot of false predictions. Then the precision is really low. And you can see here the combination measurement is really bad. It's like 0.33. So that measure is the minimum number is 0, the maximum number is 1. Our model is able to do this performance, so we can reach the precision up to 0.88, which is a lot better than this one. And our F-score is 0.76. We still miss a lot of events. Somehow the model is unable to pick it up because actually in crowdsourcing data, there are actually a lot of noises in it. Okay, so next, when we predict the data, I'm trying to understand what's happening in it instead of just providing the prediction. And the idea is I want to understand what's the environmental factors that matter the most and what's their joint effects. So remember, these are the input and output of the data. Before that, we use a model. I call it black box model because it's pretty hard to analyze. We don't really know what happened inside the model. It's pretty hard to understand how that makes decisions. So instead, I take only a part of the data and then train a white box model. White box model means something that we can easily analyze it. This part, I'm just using the knowledge that I get from the community members. So I talked to several people in the community to know that actually VOC, volatile organic compound, has an effect on smell events. Also, from the text analysis, I found that hydrogen sulfide is really important because people are mentioning it. So I just select it. And then for the samples, remember I talked about the yeses. There are 8% of yes and 92% of no's. Somehow I use a way to select a group of samples that are similar to each other, and I use that in my explanation. So the details for selecting these samples, these positive samples, and then the predictors are in my document. Now I'm just providing the high-level concept. I'm going to jump to the conclusion immediately. So my model is able to explain about health of the smell events, which is a joint effect of wind direction and hydrogen sulfide. I'm going to talk to you about patterns right now. So this is actually the pattern. When we are looking at the model, so the model is actually a decision tree. We can trace it from the top to the bottom. The first node is this one. It's the parkway east wind direction in the north and south direction multiplied by the Liberty monitor 2 hours ago. That's the first node. That usually means it's the most important one. And then the second node is the interaction effect of the Lawrenceville monitoring station multiplied by the H2S reading. That one is in a east and west direction. I'm just plotting 3 levels of the tree. There are a lot of more data, but basically after that, they are just combinations of wind directions. So this actually forms the pattern. If you look at that, that actually means if there's an emission from that monitor station, if it's detecting some H2S, and the wind somehow matches the pattern, then the air could be trapped in Pittsburgh areas, and then we get a lot of smell reports. So that's basically the pattern inside the data that I am able to find it, but I'm only able to explain about half of them. For another half, there could be noises, like wood smoke, something else. After I deployed the system, I did a study to understand the impact of the system. So it's a survey study. The survey tool is developed by Cornell Lab of Ornithology. It's a validated tool. So we measure 2 things. One is self-efficacy. Another thing is motivation. So self-efficacy means if the community is confident in the goal that they can achieve. Here is the result. We found increases in the self-efficacy in about 1 Likert scale. Another one is the motivations. So we ask internal motivation and external motivation questions, and we found that the motivations are mainly driven by internal factors. So external factors are like rewards or fames that people want to get. Internal motivations are more like they want to contribute data. They think this is good. To go further to understand the motivations, we actually look at open response fields, and we found about 36% of participants mentioned that the system allowed them to collect data easily and contribute scientific evidence. So for example, they feel that they can contribute to taking data, And now they don't have to call the health department because they can easily report data by using the system. About 6 participants mentioned altruism as the main motivation, which is the concern of the welfare of others. For example, there's one comment about that the participant used the system to raise other, or to demonstrate this to other people and show how they can use it to raise their awareness. Because there are a lot of people live in the area that has pollution for a long time, and to them this like normal, and they don't really sense the pollution anymore, and that's dangerous. The second one is about building momentums in the air quality community. So for new activists, they can use the system and they can see that there are a lot of people also concerned about the question of air quality. So they are not alone. About 4 participants, which is 16 of them, mentioned that the tool is good for validating their personal experience. For example, now they can use the tool and see, oh, they are not alone. And it validates and confirms what they are seeing. Because when they submit it, they cannot check the app and see if other people also experience the same problem. About 8% of people use personal resources to help promoting the system. For example, one participant ran a Google AdWords. Another person actually print the screen and bring them to public meetings to get the attention of regulators. Okay, so now I'm going to sum up with design implications. There are 3 design implications here. The first one is, I think it's important to treat community members as co-designers, like what I mentioned before, not tools or sensors. And I also want to emphasize these 2. Citizens as scientists is one direction, but I want to emphasize the importance of scientists as citizens. So we are also part of people who are also experience the problem. So it's also important to think about this way. Also, it's important to ask about what the community really needs, but not what the researchers think the community needs. These 2 are really different. So when we design the system, it's important to attend community meetings and then talk to people and then understand what people really need. For example, in the Shiningo Channel project, which is the air quality monitoring system, we actually have several people in the lab attend the community meetings, show them how the system works, developing the features with them that suit their needs. The Smell Pittsburgh, actually the smell ratings are designed together with the community, because the community, they know the ratings about exactly what happens of these ratings, so they were able to come up with this. Also, for me to identify the joint effect of hydrogen sulfide and wind direction, I actually use the community knowledge. So these are the knowledge that I get when I meet with people during like informal meetings. The second one is about contextualizing scientific evidence. So it's about forming the context by using evidence from different perspectives. It's important to integrate both types of data, from human-generated data or machine-generated data. For example, in the air quality monitoring system, I talk about how I integrate sensors, reports, and videos, so community members can use it to tell stories. The second one is, in the Smell Pittsburgh project, I talk about how to not just performing prediction, but also understand the structure of the data, the implications in it. So that's something that I did before for interpreting the patterns about the hydrogen, sulfur, and wind direction. The third one is to use computer vision or some other ways to automate the tasks when people are collecting the evidence. And that's actually in the air quality monitoring system. It's impossible, or maybe not impossible, it's like really difficult to collect all the evidence by looking at all the images. Somehow we can automate this and speed this up. The third one is about evaluating the impact of the system. It is important to think about, is the system influential rather than is the system useful. I'm not saying useful is not important, but I'm just saying in thesis I care more about is the system inferential. So when people talk about evaluations of a interactive system, some people refer to usability. And usability actually means if the system is effective in helping people completing a task. So it's like how much time do you need to generate an image? And that's as the measurement of a usability. But right now I care more about the impact, which is does the system actually impacts the community in some way? And it turns out it is difficult to evaluate because if we want to say if when we deploy the system, it actually influences the community in some way, then we are making a causal statement. And that's something that requires experiments. Like we have to do a randomized experiment to actually select a group of people that has access to the technology and another group of people that has no access to the technology and doing this and all at random. And this will cost a lot of resources. Also, it could be non-ethical for doing this. So instead, I'm asking a question about does the community think that the system is influential, or how can the system be influential? So that's why I'm doing all the studies after deploying the system. In the air quality monitoring project, I found that both manual and automatic approaches are both important. So I won't recommend automate everything because it is important for people to actually participate in the project and actually use the system to generate images to see like the complexity in the problem. And then later on we can automate this for them. The second one is in the survey study of Smell Pittsburgh. I actually found that the system allows people to contribute data easily and also validate their own experience and also altruism and motivations. So these are important for us to do another design iteration to like design another system features. So thank you for coming, and I would like to thank my committee members and all the lab members and also the ACAN and also Ryan from the GCC. He helped me a lot in writing the thesis and also my wife. Thank you.